Okay, well, welcome everyone to another TCS Plus talk. Today we have Shuai Zhao from University of Wisconsin, although he recently moved to Oxford to talk to us about a dichotomy for real Boolean Holland problems. Yeah, so please feel free to unmute yourself to ask any questions. And yeah, I think that's all. Please take it away.
Yeah, thanks, Eric. Thanks for the introduction, and thanks for inviting me to give this talk. Thanks, everyone, for attending my talk. Feel free to interrupt me at any time if you have any question. So today, I'm going to talk about our recent result on the complexity classification of counting problems. So it's a dichotomy for real-valued Holland problems on the Boolean domain. It's a joint work with my PhD advisor, Professor Jingyi Cai. So Holland problem is a framework for counting problems. Such a problem is parameterized by a set of Boolean constraint functions, also called signatures, denoted by script f. Each signature f, small f of variety n, is a map from the n-dimensional Boolean space to the complex field. An input of the Holland problem specified by this script f, this signature set, is a graph where each vertex is labeled by some signature, small f from this signature set, which has arity equal to the degree of the vertex. For this graph, we consider all 0, 1 edge assignments. So for each assignment, we get an evaluation, which is the product over all signatures, is a product of labeled signatures over all vertices. The output of this problem is the sum of products over all edge assignments. So there are 2 to the power of number of edges, many possible assignments. So this is the sum of product computation. Now let's see an example. A perfect matching of a graph is a set of edges such that for each vertex, exactly 1 edge incident to it is selected in this site. So in this graph, the set of red edges is the perfect matching. We want to count the number of perfect matchings of a graph. This problem can be expressed as the Holland problem parameterized by exact1 functions. Here is a definition for exact1 function. This function takes value 1 when the input has Hamming weight 1, and it takes value 0 otherwise. So the Holland problem specified by all exact1 functions is the problem of counting perfect matchings. Why we are interested in Holland problems is a very expressive framework for counting problem. So problems expressible as Holland problems include counting graph homomorphisms and counting constraint satisfaction problems. These are the 2 well-studied frameworks for counting problems. But beyond these 2 frameworks, as we just said, counting perfect matchings and counting matchings can also be expressed as Holland problems. Other problems include counting weighted Eulerian orientations, and also computing the partition function of many models from statistical physics. For example, the famous 6-word model and 8-word model. So moreover, it's proved that counting perfect matchings cannot be expressed by counting graph homomorphisms, even with any complex weights. So Holland problems, they are probably more expressive. For an arbitrary signature set script f in a large class, we want to classify the complexity of the Holland problem specified by this signature set script f. So such a classification is usually stated as the dichotomy theorem. So for a large class of signature sets f, the Holland problem, is either polynomial time computable or it's Sharpe hard with nothing in between. The Sharpe class is a quantitative version of the NP class. It was introduced by Holant in 1979. By a straightforward adaptation of Lander's theorem, we know that there is no dichotomy for the Sharpe class in general. However, for some counting frameworks, including counting graph homomorphisms and counting CSP, defined over the general domain, 4 complexity dichotomy have been established. While for Holland problems, even restricted to the Boolean domain, there are only limited results. So now let's see some of these results for Holland problems on the Boolean domain. So the first result is that a dichotomy was first proved for complex valued Holland problems when all signatures are symmetric. Well, we say a signature is symmetric if its value only depends on the Hamming weight of the input. While for the asymmetric case, some dichotomies were proved for complex valued Holland problems by assuming some actual signatures such as Holant star problems and Holant C problems. So Holant star problem is a Holant problem where all unary signatures are assumed to be available. And the Holant C is a Holant problem where two pinning unary signatures are assumed to be available. So these are the two pinning unary signatures. So we assume that in this Holant C problem, we always we are free to use these two signatures. Without assuming any actual signatures, a dichotomy was proved for non-negative valued Holant problems. And there are also some dichotomy results for some special cases of Holant problems, such as 6-vertex models and 8-vertex models. These models are Holant problems parameterized by a single special 4-array signature, while the 8-vertex model is more general than the 6-vertex model. The 6-vertex model is also a basic case of counting weighted Eulerian orientations. Recently, a dichotomy was proved for accounting weighted Eulerian orientations by assuming some symmetry assumption. This is a result with Matt Weiser and also a collaborator, Zhiguo Fu. And also together with Fu, we also proved a dichotomy for real-valued Holant problems where a signature of orderarity is available. Now in this talk, I'm going to present our recent result, which is a full dichotomy for all real-valued Holant problems without making any assumption. Now here we give the following picture as a partial map for the classification program of Holant problems. So the starting point is the dichotomy for counting Boolean CSP. Roughly speaking, there are two directions from this dichotomy. One is to prove dichotomy results by assuming some actual signatures are available. So for example, Holant star, Holant C. There is also a class of Holant problem which is called Holant plus, where we assume 4 unary signatures. And the other direction is to prove dichotomy results for some special cases of Holant problems, such as 6-vertex models, 8-vertex models, and counting Eulerian orientations. The dichotomy for real-valued Holant problems is built on all of them. But as you will see, this is an arduous journey with many wholly unexpected obstacles. Now, before we start the journey, we first introduce the following classes of tractable signatures. The first class denoted by this script T. This is a set of tensor products of unary and binary signatures. So if a signature is in T, then it can be decomposed as a tensor product of a bunch of unary signatures or binary signatures. There are also product type signatures, affine signatures, and local affine signatures. They are denoted by P, A, and L.
Sorry, yeah. What is that? What is a signature? What's the? It's just like a string.
It's just a constraint function. It's just a function from the, if a signature has arity n, it's just a function from the n-dimensional Boolean space to any complex value. But in this talk, we focus on real value signature. Awesome. Yeah, a signature is just a constraint function. Okay. And so we will give a few more details regarding the signatures later when we use them. But the class of the set of tensor products of binary and unary signatures will be used commonly in this talk. Here, transformable means that these signatures are still tractable after a holographic transformation. Well, it's known that the Holant problem specified by this signature set script f is tractable if this f satisfies this tractability condition. And this condition actually holds for complex valued signatures. Well, what we will show is that the Holant problem specified by a real valued signature set script f is sharply hard if this set does not satisfy the above tractability condition. So thus we get a dichotomy. So if it satisfies this condition, then it's tractable. Otherwise, it's sharply hard. Now, in order to prove sharply hardness, we need to build polynomial time reductions. So a commonly used approach is Gadget construction. Now we say a signature, small f, is realizable from a signature set script f by Gadget construction if there is a graph with some internal edges and dangling edges, such that labeling vertices in this graph with signatures from the signature set script f, the graph G defines this small signature, this small f, by its sum of products with dangling edges as variables. So for example, if we take a look at this graph, it has 5 dangling edges. So it defines a signature of arity 5. So this signature, this constraint function has 5 variables. And fix an assignment of these five variables. For example, if we fix the assignment of these 5 diagonal edges to be all 0, then we can get a Holant value by computing the sum of products over all edge assignments on these internal edges. So this is the value of this signature on the input, on the all 0 input, and so on and so forth. If you get another input like 0, 0, 0, 0, 1, you will also have another Holant value by computing the sum product. So this gadget defines a signature. Now, if f is realizable by the signature set script type by a gadget, then the Holant problem specified by this small f together with the original signature set script type is just equivalent to the Holant problem specified by only the signature set script type. So this reduction is quite easy. So every time when this signature small f appears in an instance, we simply replace it by this gadget, where vertices are labeled by functions from this signature set script type. A simple gadget that we will use in this talk is merging gadget. So we connect 2 variables of a signature using binary equality. So this binary equality is a function of arity 2. It's a signature of arity 2, and this function takes value 1 when its 2 variables take the same assignments. So when the 2 variables take 0, 0 or 1, 1, it has value 1, and otherwise it has value 0. Now, if we connect 2 edges using this binary equality, so we simply merge them into 1 edge because they must equal. Now, suppose that a signature has arity n, then after merging gadget, we get a signature of arity n minus 2. When the signature set script type contains a signature of odd arity, as we have said, a dichotomy is already proved. So we only need to consider the case that the signature set consists of signatures of even arity. And we suppose that this signature set does not satisfy the tractability condition. Well, otherwise we already know that it's tractable. And since it does not satisfy this tractability condition, this signature set is not a set of tensor products of binary or unary signatures. Thus, it must contain a signature small f that is not in T, which is not a tensor product of binary or unary signatures. Now we suppose that this signature small f has arity 2n. Well, clearly we know that 2n is larger or equal to 4, because if this signature has even arity, if it has arity 2, then it's just trivially a tensor product of binary signatures, because it's just a binary signature. And we want to prove Sharpe harness by induction on the arity of this signature f. The base case, if this signature has arity 4, this is the base case. And this case can be handled using the dichotomies for eight-verse models and counting weighted orientations. Well, recall that the eight-verse model is just a Holant problem with a single signature of arity 4. And here we also need to construct some complicated gadgets, and the analysis requires the signatures to be real valued. That's why that's the reason why that our dichotomy only works for real valued Holant problems. Now, in this talk, we focus on the inductive step. The general strategy is that we start with a signature that is not in T, that is not a tensor product of binary or unary signatures. And we want to use it to realize a signature of lower arity that is still not in T. So if this can be done, then by sequence reductions, we can eventually realize a signature of arity 4 that is not in T. Then we are done by the base case. So this induction is actually a standard approach to prove dichotomy for Holant problems. Well, since we want to achieve a dichotomy, we need to classify signatures of arbitrary large arity. So we need to use induction to reduce the arity to some finite base cases. And this induction approach was very successful in previous proofs for Holant problems. And in all those proofs, we usually have unary signatures. Now, when we have the unary signature, we can connect a signature of arity n with a unary signature. Then we get a signature of arity n minus 1. So if we have the unary signature, if the unary signature is available, then we can reduce the arity by 1 after each inductive step. That's why there are many dichotomies for Holant problems by assuming unary signatures. But now we can only use merging to realize signatures of lower arity. And after each inductive step, the arity, we reduce the arity by 2. Now what we want to consider the following question. Now, given a signature of arity 2n that is not in T, that is not a tensor product of binary or unary signatures, by merging, can we realize a signature of arity 2n minus 2 that is still not in T? Now we use this notation to denote the merging operation using binary equality. Well, the answer is yes, but only for signatures of arity larger or equal to 10, so at least 10. Here we still need to make some additional assumptions by using these signatures to be these signatures being real valued. But the thing is that there do exist signatures of arity 6 and 8 with extraordinary properties, which presented a formidable obstacle to the induction proof. So the induction proof does not work as usual in the case of signatures of order arity. Now here we give this picture. Now our plan is not as trivial as shown in the first picture, but we thought that we had developed all the necessary toolkit to achieve the induction proof. But however, here is the reality. So now let's take a look at the first major obstacle. We consider the following 6 array signature. So it's a function, it's a constraint function, it's a Boolean function on 6 variables, and it has this this formula. Now this signature, the support of this signature is all even weighted points. So the support of a signature is just the set of inputs on which the signature takes non-zero values. So as you can see that the support, which is denoted by this exercise sub x, this is the 0, 1 indicator function on this side on the all even weighted points. And we can represent this signature by the following matrix. Now here we use the first 3 variables as a row index and the last 3 variables as a column index. For example, the first row are entries where the variables x1, x2, x3 equals 0, 0, 0. And the second row are entries where x1, x2, x3 equals 0, 0, 1. So on and so forth from 0, 0, 0 to 1, 1, 1. And same for the columns. Now we give the following picture to visualize this matrix. In this picture, a block with orange color denotes an entry plus 1. And a block with blue color denotes an entry minus 1. And the other blocks are zeros. So for example, this orange block means that the value of on input on the all 0 input is 1. Now let's see some properties of this function f sub 6. First, we can show that it's irreducible. So it's not a tensor product at all. We cannot decompose it. We cannot factorize it. So clearly, it's not a tensor product of binary or unary signatures. So it's not in T. However, by merging any 2 variables of f sub 6 using binary equality, we can only realize 4 array signatures that are in T. So now this signature, this signature f sub 6 is an obstacle to our induction proof, because that from this signature we cannot realize a signature that is not in T by merging. And in fact, it's an obstacle that we have to deal with. Now we have the following lemma. We suppose that this signature site, script type, does not satisfy the tractability condition. And we assume that it contains a signature of arity 6 that is not in T. Then either we can show that this problem is already hard directly, or we can show that this signature f sub 6 is realizable. So it's realizable means that we can have the reduction from Holland specified by f sub 6 together with the original signature site script type to the original Holland problem. So now we need to prove that this problem, the Holland problem specified by the original signature site script type together with this signature f sub 6 is sharply hard when this signature site does not satisfy the tractability condition. So if we can show this, then we are still done with this induction proof. Now we just include this the case of arity 6 as the base case. Now let's consider what kind of other signatures can be realized from this signature f sub 6 by gadget construction. First, by merging two variables of f6 using this binary equality, we can realize all four binary signatures. So these are four binary functions. Now, this is the binary equality, and this is the binary disequality. So this function takes value 1 when its two variables take different assignments. And this is like the negative version of the binary equality. So it takes value 1 if it takes non-zero value when its two variables take the same assignments, but it takes value 1 when the two variables take assignment 0, and it takes the value -1 when its two variables takes the assignment 1. And this is the negative version of the binary disequality. We call them binary Bell signatures because that they are related to Bell states in quantum information theory. As we can see, these are the four Bell states in quantum information theory, and they can respond to the Bell binary signatures perfectly. So here we just list you can think that we list the truth table of these four signatures. So for this binary equality, it takes value 1 if the input is 0, 0, and 1, 1, like so on and so forth. Now, after we get all these four binary signatures, we can also use them to do gadget construction. And in particular, we can use them to connect two variables of the signature of the original signature f sub 6. So now we consider all four array signatures realizable from this special signature f sub 6 by merging its two variables using any of these four binary signatures. So this means that we merge the variables xi and xg of f sub 6 using the binary signature b. So b can be any one of these four binary signatures. Now, if there is one that is not in T, then the induction proof would still work, because as long as we can get a signature of every four that is not in T, then we are done. This is already proved for the base case. However, this signature f6 satisfies the following Bell property. Now, we see a signature satisfies the Bell property if for every pair of indices I and G, and for every Bell binary signature B, the signature realized by merging variables xi and variable xg of f using this Bell binary signature B is a tensor product of Bell binary signatures. So here we use this script b to the power of the tensor power of script b to denote the set of signatures that are tensor products of Bell binary signatures. So this means that by merging this signature, so this we said that f6 satisfies this property. So by merging this f6 using Bell binary signatures, we can only get tensor products of Bell binary signatures. So we cannot get any signature that is not in T. And by connecting f6, well, by modifying the signature f sub 6, we can actually generalize it to a family of script f sub 6. So also we can realize like other 6 array signatures that satisfy the Bell property. So all signatures in this family script f sub 6, they all satisfy the Bell property. And we use this script b to the tensor power of 3 to denote the set of tensor products of 3 Bell binary signatures. So signatures in this site are signatures of array T6. And together with this family script f sub 6, they capture all 6 array signatures that are a series obstacle to our induction proof. So what do we mean by a series obstacle? So we have the following lemma. Suppose that the signature set script f does not satisfy the tractability condition. And if it contains a non-zero signature of array at most 6, and suppose that this signature is not a tensor product of Bell binary signatures, and it's not in this special family script f sub 6, then we can show that the Holant problem specified by this signature set script f together with this special signature f sub 6 is already shall be hard. So signatures in this union are the only signatures that we cannot handle. All other cases are already done. We can already show that they are shall be hard. So this is the case that we need to handle. And So with this lemma in hand, now we want to consider that what kind of signatures we can be realized from this f sub 6 and this signature site from all binary signatures. Well, remember that we already said that either the original problem is already sharply hard, or this special signature f sub 6 is realizable. Once we have this signature f sub 6, we can realize all 4 binary signatures by Gadget construction from this signature f sub 6. So we can do Gadget construction using these signatures. Now, if we could realize a signature of arity at most 6 that is not in this union, that is not a tensor product of binary signatures, that is also not in this special family, this scriptal f sub 6 that satisfies the Bell property, then there would be a somewhat more straightforward proof by the previous lemma. And actually, this is also a common approach in many previous proofs for Holland problems. Well, for some signatures for which the induction proof fails, here for this signature, for this f sub 6, the induction proof does not work. Usually, this signature, they have a very special structure from which we can realize some signatures that give us the Sharpie hardness directly. So here we also want to get the Sharpie hardness directly by Gadget construction using this signature f sub 6. Well, however, after many failed attempts, we believe that there is a more interesting reason why this approach cannot work in this case. We conjecture that all signatures of arity at most 6 realizable from this special signature f sub 6 and all 4 binary signatures, they are still either tensor products of binary signatures, or they are in this family that satisfy the Bell property. So this signature f sub 6 has a closure property. So now we have to come up with another way to prove the Sharpie hardness. So any questions so far? Okay, now we have to come up with another way to prove Sharpie hardness. Now, since we know that the signature site does not satisfy the tractability condition, well, recall that the tractability condition includes 4 classes. The first class is T, which is a tensor product, which is a set of tensor products of binary or unary signatures. There are also other 3 classes of tractable signatures. They are product type, affine signatures, and local affine signatures. Now, since this signature site does not satisfy the tractability condition, it's not a set of affine signatures. So it contains a signature that is not in affine. Now we give some properties of affine signatures. If a signature satisfies, if a signature is an affine signature, then it satisfies the following property. First, all non-zero entries of this signature have the same null. Secondly, the support is an affine linear space. We will prove the Sharpie hardness of the Holland problem specified by the original signature site script f, together with this special signature f sub 6 and this and the signature set of all binary signatures by induction on the arity of this non-affine signature. Now, still recall that we have said that either the Holland problem is already Sharpie hard, or f6 is realizable. And once f6 is realizable, all binary signatures are also realizable. So we only need to prove Sharpie hardness for this Holland problem. And we will prove the Sharpie hardness by induction on this on the arity of this non-affine signature. Now, why do we pick a non-affine signature? Well, we can show that this union, which is a serious obstacle to our induction proof, to our hardness proof. Now, all signatures in this class, they are affine signatures. So now, if we can realize a non-affine signature of arity no more than 6, then we have a signature that is out of this union, and we are done per lemma. So this is the base cases for the induction proof on the arity of non-affine signatures. Now we consider the inductive step. Given a non-affine signature of arity at least 8, because the case of arity no more than 6 is already done. So we consider if we have a non-affine signature of arity at least 8, by merging f, now we can use all these 4 binary signatures to do merging. And can we realize a non-affine signature of low arity? So still, if this could be done, Then by a sequence of reductions, we can eventually realize a signature of arity no more than 6. That is not affine, and we are done. In other words, suppose that the signature F satisfies the following property: that by merging this signature using arbitrary binary signatures, by merging any two variables of this signature using any binary signatures, we can only get affine signatures. Then can we show that this signature itself must also be an affine signature? Now recall that an affine signature, it satisfies two properties. The first is that all its non-zero entries have the same norm, and its support is an affine linear space. So we will prove that this signature F itself is an affine signature by the following 3 steps. The first step, we ask whether all non-zero entries of F have the same norm. Well, the answer is yes, but only for signatures of arity at least 10. So there exist signatures of arity 8 that have entries with different non-zero norms, such as by merging them using binary signatures, we can only get affine signatures. For example, if you can look at the two signatures, G sub 8 and G prime sub 8. Well, this signature, they have entries. It has entries of norm 1. It also has entries of norm 1 minus 4, which is equal to 3, which has norm 3. I will not go into the details of these signatures, but here you can see a special signature F8 appears in these two signatures. Later we will see it again. But here for these two signatures, fortunately, we can use them to realize 6 array signatures that are not in this union by Gadget construction. So then we are done for this case, because if it turns out that this signature has this form, then we can show that it gives the Sharpe hardness by realizing a 6 array signature that is not in this union. Then we consider that whether this signature has an affine support. Still, well, here the answer is yes, and there's no counterexample. So this is the only step in the whole proof. This is the proof of like 92 pages. This is the only step in the whole proof that goes smoothly without a counterexample. And well, here we achieve this step by proving the following interesting result for graphs. And I think this result should be of independent interest. So let's take a look at this result regarding graphs. Now let's K sub n be the complete graph on n vertices. It's a simple graph with no loops. It's just a complete graph. And we see this complete graph has a tripartite 2 partition if there exists 2 complete tripartite subgraphs T1 and T2. Well, a tripartite subgraph is complete if all its vertices can be divided into 3 sides, and all edges between vertices in different sides are in this graph. And we see this complete graph has a tripartite 2 partition if the edges of these 2 complete tripartite subgraphs is a partition of the edges of the original complete graph. And we can show that such a complete graph has a tripartite 2 partition if and only if it has vertices. It has the number of vertices is less than or equal to 5. Well, in fact, in the proof of the real Holant dichotomy, we proved many interesting results for graphs. Later, we will see another one. Now, finally, by assuming that we already proved that F has affine support and all its non-zero entries have the same norm. Now we ask whether F itself is an affine signature. And well, as you can see that this is already a quite strong requirement. And we thought that there was no F that would satisfy this property except it's an affine signature. Well, however, our conjecture is true only for signatures for arity at least 10. So there exists a non-affine signature of arity 8, such that by merging it using binary signatures, we can only get affine signatures. Well, as you can see, this signature, all non-zero entries of this signature, they have the same norm. They all have norm 1, and the support of this signature is, or we will go in. The support of this signature is same as the support of this signature F sub 8. We will go into this support later. But still, fortunately, for this signature, we can realize 6 array signatures. We can realize a 6 array signature that is not in this union. That is not in the union of a tensor product of bio-binary signatures together with that special family that satisfies the bio property. So from this signature, we can also get the sharp hardness directly. So now, so now let's summarize the case of 6 array signatures. Now, by the induction proof on non-affine signatures, we prove that this problem, the Holland problem specified by the original signature set script f, together with this special signature f sub 6, and the all 4 bio-binary signatures, this problem is sharply hard when the signature set does not satisfy the tractability condition. And finally, we can show that okay, the original Holland problem specified by a signature set script f, which does not satisfy the tractability condition and contains a 6 array signature that is not in T, is sharply hard. Or recall that previously we showed that this problem either it's sharply hard, or we can realize this signature f sub 6. And once f6 is realizable, we can also realize all 4 bio-binary signatures. And we showed that this problem is sharply hard. So the original problem is sharply hard. So now we are done with the case of 6 array signatures. So far, any questions? Okay, now let's consider the case of 8 array signatures. Now we consider the following signature f sub 8. Now this signature is a 0, 1 value function. Well, as you can see, it has an affine support. Now here is it has an affine support means that its support is an affine linear space. Now here, the support of this signature is just a solution space of these linear equations. So it's definitely a linear space. And we use the following picture to visualize this signature. Now here, a block with orange color denotes an entry +1. Other blank blocks are zeros. So this matrix is quite sparse. And this signature satisfies what we call the butterfly property. So if we look at the support, if we look at all these blocks with orange colors, now here in this matrix we use the first 4 variables as the row index and the last 4 variables as the column index. And as you can see, the sum of the first 4 variables must be even. So they are all 0, like 0, 0, 1, 1. And also the sum of the last 4 variables, they are also even. And the assignment of the first 4 variables are either identical or complement of the assignment of the last 4 variables. Like you can see 0, 0. If the assignment on the first 4 variables are 0, 0, 0, 0, then the assignment on the last 4 variables must be all 0 or all 1. Like if it's 0, 0, 1, 1, then it must be 0, 0, 1, 1 or 1, 1, 0, 0. So the first 4 variables and the last 4 variables can be viewed as 2 wings of the butterfly. Well, actually, in fact, we can arbitrarily pick 3 variables. Then by the support, there is a unique variable that is fully decided by these variables. Like for example, if we pick these 3 variables like x1, x2, x5, then x6, the variable x sub 6 is uniquely decided by these 4 variables, by these 3 variables. Then together, these 4 variables, they form a wing of the butterfly. And then you can divide these 4 variables into 2 sides. One side is these 4 variables, and the other side is like x3, x4, x7, x8. Then they form 2 wings of the butterfly. So this signature has a high degree of symmetry. Now let's take a look at some properties of this signature. Still, this signature is irreducible, means that it's not a tensor product, and so it's not in T. It's not a tensor product of binary or unary signatures. However, by merging these signatures, by merging any 2 variables of this signature f sub 6 using the binary equality, we can only get signatures that are tensor products of binary signatures. So still, this signature is an obstacle to the induction proof, because here the induction does not work anymore. Because for this signature, we cannot realize a signature of lowarity that is not in T. And in fact, this signature satisfies the following strong bio property. Well, we see a signature satisfies the strong bio property if for all pairs of indices I and G, and for every bio-binary signature B, the signature realized by merging variables xi and xg of f using this B is a tensor product of the Bell-binary signature B. So here, this Bell-binary signature B is the same signature B that is used for the merging gadget. So if you use B to do the merging gadget, you get a tensor product B itself. And here we list the factorizations of all signatures realized by merging variables of f sub 8 using a Bell-binary signature B. And here this I and G means the Bell-binary signature B on variables xi and xg. This B depends on which B you used for the merging gadget. And now, as you can see that each binary signature appears exactly 3 times, and it appears in 3 disjoint pairs. Actually, it appears in 1 row. For example, the binary signature 3, 4, it appears in the merging gadget after merging. It appears in the signature realized by merging variables 1, 2. It also appears by in the signature by merging 5, 6 and by merging 7, 8. In fact, we can show that given a signature variety 8, if by merging it using Bell-binary signatures, we can only get tensor products of Bell-binary signatures. Then we can show that it itself must be a tensor product of Bell-binary signatures unless it has this particular factorization table. And in fact, we first proved this result, and we showed that there was no signature that could have this factorization form. And this is so strange. However, after many attempts, we realized that there is something hidden behind this table. And this is how we discovered this signature f sub 8. Now here, this signature f sub 8 is actually discovered by analyzing the maximum independent set of a special family of graphs. So here it comes again. We proved the dichotomy for Holant problems by analyzing some results for graphs. Now we define the following graphs, G sub 2n as follows. Here the vertex site of this of the graph G sub 2n is a set for all even weighted points in the 2n dimensional Boolean space. And 2 points, they are connected by an edge if and only if the Hamming distance is 2. Then this is the support of the signature f sub 8, which denoted by T. This T is just the unique maximum independent set of the graph G sub 8. Well, we say it's unique up to an automorphism of this graph. And moreover, if we let alpha of G sub 2n be the independence number of this graph G sub 2n, well, this is the size of a maximum independent set of this graph. Then when 2n equals 8, the independence number is just 1/8 of the number of vertices. And when 2a is larger or equal to 10, then the independence number is strictly less than 1/8 of the number of vertices. This actually might be a reason that why all these special signatures, they appear only when the arity is 8. Now we're back to the proof of the Sharpe hardness of the Holant problem. Still, we can show that the original Holant problem is Sharpe hard directly, or we can realize this signature f sub 8. And we can also prove that the Holant problem specified by the original signature site, together with this special signature f sub 8, and all 4 Bell-binary signatures, we can show that this problem is Sharpe hard, similar to the proof of the Holant problem specified by this signature f sub 6, together with all 4 Bell-binary signatures. So still, Bell-ion induction on a non-affine signature. So if we could realize all 4 Bell-binary signatures from this signature f sub 8 by Gadget construction, as we did for that signature, for the signature f sub 6, then we would be done, because then we can just using the hardness of this problem, and we have the reduction from this Holant problem to the original Holant problem. Then we are done. However, this signature f sub 8 is even more resistant than f sub 6. Well, as you can see that since this signature has even arity, well, it has even arity means that all its non-zero entries are uneven weighted inputs, and all its entries are non-negative. Then by Gadget construction, all signatures realizable from this signature f sub 8, they all have even parity, and they all have non-negative entries. So these three Bell-binary signatures cannot be realized from this signature f sub 8 by Gadget construction. Now, well, these two, like the negative version of binary equality and the negative version of the binary disequality, they all have negative entries, so they cannot be realized from this signature f sub 8. And the binary disequality, it has odd parity, and so you cannot realize it by Gadget construction using this signature f sub 8. So basically, from this signature f sub 8, we cannot realize anything useful. We actually conjecture that all signatures realizable from this signature f sub 8 of rt no more than 8, they are either tensor products of binary equality signatures, or it's just the signature itself. So this signature has a very strong closure property. So now at first we would like to realize a signature by Gadget construction. Now, if we can realize binary signatures by Gadget construction, then we can use it for an arbitrary number of times. Just each time it appears, we just replace it by a Gadget. Now we introduce the Holant problem with limited appearance. The Holant problem, specified by the signature site script f, together with this small f with limited times k, this problem contains all instances of the original Holant problem where the signature appears at most k times. So in this problem, we limited the appearance of this signature f by k times. Now the following lemma shows that in order to realize of Bell-binary signature, now still our goal is to realize all Bell-binary signatures, but we have shown that we cannot realize them using Gadget construction. So we have to come up with another way to realize them. Now the following lemma shows that in order to realize a Bell-binary signature, we only need to realize it for no more than twice. We do not need to realize it an arbitrary number of times. Now, and the proof is crucially based on the strong Bell property. Well, this is the property that makes this signature f8 so difficult to handle, but we can also use it to give a novel reduction. Now we consider an instance of this problem where this signature appears more than where this Bell-binary signature B appears at least 3 times. Well, since that this signature f sub 8 satisfies the strong Bell property, so by merging this signature using one copy of B, we can get a tensor product of 3 copies of B. So we can use one B to produce. We can use one copy of the Bell-binary signature B to produce 3 copies of B. So thus, replacing 3 occurrence of B in this instance by this merging Gadget using B, we can reduce the number of occurrences of B by 2. So eventually, we can reduce this case, this instance to an instance where B only appears no more than twice. And once we have this reduction, then we show that we can realize Bell-binary signatures for at most twice with a non-constructive reduction. And then we have this reduction, the reduction from Holant problem specified by the original signature site script f, together with the special signature f sub 8, and all Bell-binary signatures to this Holant problem. And finally, we can show that okay, this Holant problem specified by a signature site script f that does not satisfy the tractability condition, and it contains a signature of rt8 that is not in T. We can show that this problem is sharply hard. So now we are also done for the case of 8-array signatures. Now we can finish the proof for the dichotomy of real Holant. We can finish the proof of the real Holant dichotomy. Still, we only need to prove that this problem is sharply hard when the signature site does not satisfy the tractability condition. So we only need to prove the sharply hardness part. And if it contains a signature of orderity, then we are already done. So otherwise, this signature site consists of signatures of unarity. And since it does not satisfy the tractability condition, it contains a signature that is not in T. And suppose that this signature has arity 2n, we know that it has the arity is at least 4. And if the arity is equal to 4, 6, or 8, then we are done by the above lemmas. So for this induction proof, we have to prove base cases for 8. And when the signature has arity larger or equal to 10, then as we have said, the induction proof works. So we can eventually realize the signature of arity no more than 8 from F. So this finished the proof of the real Holland dichotomy. So now we proved a dichotomy for real valued Holland problems. Well, the ultimate goal is definitely a dichotomy for complex valued Holland problems. Well, to achieve this result, we think that at least there are 2 steps we need to go. First, we need to generalize the dichotomy for real valued Holland problems where a signature of all arity is available to the complex valued setting. So here we still assume that a signature of all arity is available. Secondly, we also need to prove a dichotomy for counting weighted Eulerian orientations. Well, we use this sharp EO to denote counting weighted Eulerian orientations. We need to prove dichotomy for this problem without assuming a symmetry which is called error reversal symmetry. So now we have a dichotomy for EO with this assumption. This is an assumption that is usually assumed in statistical physics. And also these problems with a double box, for these problems that with a double box, we have a complete complexity classification for these problems even for the planar setting. Well, for example, for the complex valued symmetric Holland problems, each problem is either tractable for all general graphs, or it's tractable for planar graphs, but sharply hard for general graphs, or it's sharply hard even for planar graphs. Well, the famous example that are tractable for planar case, but hard for general is counting perfect matchings. So counting perfect matchings is sharply hard for general graphs, but it can be done in polynomial time by the famous FKT algorithm in polynomial time for planar graphs. So we may also consider that are there other problems that are there other counting problems in the Holland frameworks that are tractable only for planar graphs. But there is still a long way to go in order to achieve a full complexity classification for Holland problems on the planar setting. So this is my talk. Yeah, thanks. Yeah, thanks. Any questions? Yeah.
Thanks, Shuai.
Yeah.
So I have a question. Is most of the work here was involved in coming up with the reductions?
Yes. Yeah, because we want to prove sharply hardness.
And so all these, they come with like matching polynomial time algorithms to when they're not in these classes?
In which classes you mean, like?
In the, I mean, whenever you can't prove the reduction.
Yes.
You have also a corresponding algorithm to solve the Holland problem?
Yes. Well, as we have said that for the real valued Holland problems, the tractable party is already known. So we already have algorithms for these tractable signatures. These are like the product, for product type signatures, we have an algorithm that's based on just take the product. And for assigned signatures, the algorithm is produced by solving by Gauss elimination. So yeah, just basically you are solving a bunch of linear equations. So for all these for all these signatures that are non-tractable, we already have algorithms. And for the real valued Holland problems, we want to prove like all the Riemann things are sharply hard. So for this part, we only need to prove sharply hardness. But when it comes to complex valued Holland problems, there are new tractable things that we cannot prove reduction because that they are tractable. If we assume that FP is not equal to sharp P, then you cannot prove that it's sharply hard. Then, and for these new problems, we will discover like new algorithms. So usually like the strategy is that we first try to prove that they are sharply hard. But we managed to prove that, but maybe after many attempts, we found that, okay, it's hard for us to prove that it's sharply hard. Then we may think that, oh, they might be tractable. And then we may think that we may try to devise some algorithm for these problems. Yeah, but for the real value setting, there's no new algorithms.
Are there natural counting problems which cannot be expressed as a real Holland problem, but can be expressed as a complex Holland problem?
Yes, there are problems that cannot be expressed by real value Holland problem, because so first there are new tractable things in the complex value setting. So these algorithms are these problems are tractable by a new algorithm. So these problems definitely cannot be captured by this real valued Holland problem setting, because that by the real Holland problem, these signatures are short hard, but they are only tractable when we allow to take complex values. And on the other hand, the counting orientation problems with this symmetry called arrow rule symmetry, they correspond to the real valued Holland problems exactly. So there is a one-to-one correspondence between counting orientations with arrow rule symmetry to a special class of real valued Holland problems. So basically, real values can respond to this arrow rule symmetry after a holographic transformation. But for complex values, you have problems that does not satisfy this arrow rule symmetry. And in physics, in statistical physics, there are problems, like there are 6-word models that does not satisfy this symmetry. And these problems cannot be captured by real valued Holland problems. So there do exist problems that can be expressed by real valued Holland problems. So it's interesting to extend the dichotomy for real valued Holland to complex valued Holland.
Okay, thank you.
Okay,
Any
so
other
I'll
questions?
take us off the recording. We can still hang out for a bit.
Okay, sure.
But thanks again, Shuai, for
Yeah, thanks. Yeah.
doing the talk.